We're going to talk about the standard minimization problem. A linear programming problem is in standard minimum form if the following conditions are satisfied. First of all, the objective function is to be minimized. Second, all variables are non-negative. And third, all the remaining constraints are stated in a specific form. A1 times Y1 plus A2 times Y2 all the way up to an times yn is greater than or equal to b, with b being greater than or equal to 0. We'll assume in the coefficients in the objective function are positive to simplify this presentation. So that standard minimization problem and the standard maximization share an interesting characteristic. Any solution of one problem automatically provides the solution of the other problem. Each problem is called the dual of the other problem. So the standard minimization problem is the dual of the standard maximization problem, and vice versa. To see this connection, let's solve a minimization problem graphically first, and then we'll look at the corresponding dual maximization problem and solve it with the simplex method. Once we have that, we'll look at the solutions and it'll be pretty apparent what the connection is. So we're going to minimize W equals 5 times Y1 plus 2 times Y2, subject to 2 times Y1 plus 3 times Y2 greater than or equal to 6, 4 times Y1 plus Y2 greater than or equal to 6, Y1 greater than or equal to 0, and Y2 greater than or equal to 0. You can see that this meets all the requirements of a standard minimization problem. If I go ahead and graph out the inequalities, the red line that you see here is just 2y1 plus 3y2 equals 6, as long as I label y1 horizontally and y2 vertically. The blue line here is 4y1 plus y2 equals 6, and when I do the proper shading here, I find that I get a feasible region out here. So I have a corner point at 0, 6, I have a corner point at 3, 0, and another one at 6/5, 6/5. So to finish this problem graphically, I need to go ahead and take my ordered pairs that are my corner points and go ahead and put them into the objective function. So when I put in 3 and 0, I get 15. 6/5, 6/5 gives me 8.4, and 0, 6 gives me 12. So since we're minimizing, the minimum occurs at y1 equals 6/5, y2 equals 6/5, for a minimum value of w equals 8.4. Solving this graphically isn't a big deal. What we want to be able to do is see the big picture here. We'll have problems that have more variables, like 3, 4, or 5. We won't be able to solve them graphically, but we will be able to solve them using the dual. To find the dual problem, we need to write the standard minimization problem in an augmented matrix without the slack variables. What I'm going to do is take the objective function and write it in a matrix as 5, 2, 0. The 5 and the 2 are the coefficients on the variables, and I'm going to put that in the third row. Then I take my constraints and I write them in the first and the second row. So the 2y1 plus 3y2 greater than or equal to 6 becomes 2, 3, 6. The 4y1 plus y2 greater than or equal to 6 becomes 4, 1, 6. I have a vertical line, which represents my inequalities and my equals, a horizontal line that separates the constraints from the objective function. What we're going to do is find the transpose of this matrix. We could do this to any matrix in exactly the same way. What we need to do is to exchange the rows and the columns of the matrix that we just created. The first row is going to become the first column. The second row is going to become the second column. The third row is going to become the third column. Where I had 2, 3, 6, now that's going to become 2, 4, 5 because 2, 4, 5 was the first column. It's going to switch over to the first row and so on. So I end up with 2, 4, 5 in the first row, 3, 1, 2 in the second row, and 6, 6, 0 in the third row. Once I have that new matrix, I'm going to write it out as a linear programming problem. But I'm going to write it out as a standard maximization problem. So that bottom row that we had before, 6, 6, 0, it's going to become the objective function z equals 6x1 plus 6x2. So 2, 4, 5 becomes 2x1 plus 4x2 less than or equal to 5. 3, 1, 2 becomes 3x1 plus x2 less than or equal to 2. Notice because this is a standard maximization problem, these are now less than or equal to. In the minimization problem, they were greater than or equal to. Another key thing is notice how when I write a standard maximization problem, I use x1, x2, and z. When I do a minimization problem, I use y1, y2, and w. This way, I don't get the two problems confused.